doing, so I might as well.
So are you. Okay, talk about Telstra.
All right, let's do it.
So that GoToMeeting thing is in the lower right. You can.
Oh yeah.
I think you exit. You're going to exit the meeting.
That.
If you do that, then it shrinks the controls. There we go.
Sweet. So my account. I have a nifty 10% badge in this one. So this competition dealt with there's 18,000 IDs that they gave you, and each of the IDs has a fault severity associated with it. The goal of the competition is to predict some of these fault severities. So they give you 7,000, and there's 11,000 fault severities that you're supposed to predict. If you look at the data, so in the train and the test set, they have, in the train set you'll obviously have some of the fault severities given to you. In the test set, that column is left blank. But they also have location data in the train and the test sets. And this is a really weird variable that I struggled with for a long time to use because it didn't really seem to make much sense, like what the location has to do with fault severity. But we'll get into the data in a little bit. There are a bunch of other data files that they gave you. There's a severity type, not related to fault severity necessarily, different things. There's a log feature, a resource type, and an event type. Now, in all of these files, they contain every single ID, so there's no missing data. So every ID will have at least one severity type, and at least one log feature, at least one resource type, and at least one event type. So there wasn't really much playing around you could do with missing data, which kind of made this all about feature engineering. So I have a simple file or a simple code that I started with to just kind of try to get a benchmark for myself to be able to score like all feature engineering on. So I just treated all of these data files as if they were categorical variables. Is everybody familiar with like how you would treat a categorical variable? No? All right, so a categorical variable would be, all right, well, maybe I'll load up some data here. So this is the train data set. It's got a location column, so location 118, 91, 152. We're going to try to use these somehow. If you treat them as categorical variables, you are assuming that location 118 is completely separate and not related at all to location 117 or location 900. They're all completely separate. Okay. And the way that you tell the machine that is the case is you have to give each of these numbers a separate column. And if the location is there, then you give it a 1, and if it's not there, you give it a 0. That's the only way the machine would know. If you put it into the same column, the machine's always going to try to, like, especially with the decision tree, it's always going to try to, like, all right, we're going to say that everything above location 200 is similar and everything below 200 is similar. Right? Does that make sense?
Can you say that again?
So if you're treating it as a numerical variable, so let's say I just like stripped the location, because well, first of all, you got to give the machine a number, right? You can't give it a string. So let's say I just strip location, making it a numerical, make all these locations numerical. The machine is going to think that the magnitude of this number is meaningful in some way.
But you can treat it as a string, right? You can have a string 118, can't you?
Well, the machine is going to have no idea what to do with the string.
Okay.
I mean, it's going to. It doesn't know how.
You can code it black, you can code it orange, or whatever. You can give it a name. The machine is not able to interpret as a categorical value.
Oh yeah. So I guess there's some
you know
machines.
What I'm saying. I mean, 118, yes, has a meaning for us as a numerical.
Yeah.
But also we can put it in the code, so it can be a string.
Yeah, so I guess in that case, the machine would treat it as a categorical variable. So it would treat 118 completely different than 119, for instance. I don't know if some languages can do that. I know Python, it would probably freak out a little bit. XGBoost, yeah, I don't think that it likes that, but to be honest, I haven't tried, so it's possible.
An idea.
I came across this very recently. The pandas data frame actually has an as categorical.
Oh, does it?
But I don't think that things like scikit-learn or XGBoost will be able to use it.
Are R
Yeah.
as factor variable,
Yes.
and you can actually use it as a factor variable when you do decision tree, but you can do XGBoost things.
Can't do
like that.
XGBoost.
Yeah, you can.
And XGBoost is just, I mean, XGBoost is the way to go. Like,
Yeah.
you kind of have to, like, work within the
Yeah.
XGBoosts. All right, so yeah, just to start with, we're going to treat everything as categorical. We're going to see how well the machine can learn off of these categorical variables, and we're going to get a benchmark score, and then we're going to try to do feature engineering on that. And then we can at least measure, we can at least tell if we're improving or getting worse, if the machine does better or not. So for this first little bit, I'm just loading in the data. I concatenate the test data set with the train data set because all the other data sets contain all the IDs, and I'm eventually going to put everything all together at once. So I put the test data set with the train data set. I fill this missing column with predict. So this is what that concatenation looks like for all the 18,000 IDs. What was that sound? Oh, okay.
Can I ask a question here? It's I saw this methodology is also in Titanic and other things. People are concatenating train and test, right?
Yeah.
But is it fair to do that? I mean, test should be a data set not seen by the model.
Exactly. So you'll notice that when I do my machine learning part, I'm going to specifically take it out.
Split the train in cross validation and
Yeah. Well,
train, right?
I'm just going to I'm going to take my full data set. I'm going to say, all right, now I'm going to create a sub data set that is only train, and then I'm just going to deal with that train data set.
But for purposes of filling the missing data, which is what you're doing here, right? I mean, you have to do them.
Well, it's not. This isn't missing data. This is missing. This is something I want to predict. So this is my test column that I'm trying to predict.
But any kind of feature manipulation you'll do if you want to renormalize whatever, it's easier to do it with one data set.
That's right. Yeah, it just makes a lot of the feature engineering simpler. If you're only feature engineering with respect to the train data set, then you might introduce some leakage somewhere along the line.
In real life, you don't have a test like this. In real life, you have a train data. That's what I'm saying. In Kaggle, yeah, we are a little bit lucky here. But in real life, you have a train, and then you go apply your model.
Right.
Can't you split off some
Yeah.
just randomly? And
Yeah, so that's how you evaluate your machine learning algorithm. Is you only deal with train, you see how it's doing on the unknown part of train,
Yeah,
and then
yeah.
that's like your CV score, and then
Okay.
yeah. And so that's what we're going to try to minimize. But just for now, just to keep everything simple, I'm just going to put it all into one data frame. So I'm going to make this sparse using the get dummies. Last time we met, we talked about the get dummy trap. Bruce, do you remember that?
Yeah, I do remember that.
I was thinking about that for trees. I actually think it's bad to take out that last column for trees because I was imagining a case, let's say you have a feature with 4 variables. So you really, to know all of your information, you only need to use 3 of them, right? But if you're doing a tree method, for the tree to know if that 4th column is a 1, it needs to access each of those other columns, right?
Yeah.
And so it's going to be...
The dummy variable trap wouldn't apply in this case. It's
Right.
You've got category, which is sort of partitions of space, so it's... If you know the first 2, you know the third, sort of thing.
Well, you would for this sparse too.
I guess you
For the location, you would. Because there's only 1 location per ID. But there's 1,000 locations. So if I left out that last column, the only way it would know if it was in that last column is if it accessed 999, which the tree is never going to look at all of those at once, right?
So
And-
what are you guys saying?
So there's a get dummy trap that is really important to avoid doing when you're dealing with other machine learning algorithms that deal with a lot of matrix multiplication. I'm kind of new to this, but SVM and some of the other ones, the computer is going to take the matrix and invert it and do all this other kind of matrix multiplication on it. Mm-hmm. And if you have a column that is completely dependent on other columns, which it would be the case. Last time we talked about male and female. So if you have somebody that's either male or female, and you have 2 columns representing that, then one of those columns is completely dependent on the other column. You really only need 1 column,
So it's
right?
completely correlated.
Yeah.
The correlation is 1.
So when the computer tries to invert these matrices and do this type of stuff, it gets into trouble and it
Yeah, unless it uses pseudo inverse, which is which I mean avoids that
You're
problem.
not adding any information with the next
Exactly.
one. So the entropy is the fact. It's the
Yeah.
you don't decrease the entropy.
Right. But in this case, we technically aren't adding any information, but it makes it extremely hard for the tree to use that like information. So the trees aren't limited by this get dummy trap. And so it's just best to, I think it's just best to leave everything in there and not take out that last column. Maybe if it's male or female, maybe if it's just 2 columns you can, and it probably wouldn't have any effect, but if it's something larger, if there's like more than 10 columns, it's probably really bad to do.
So what is the last column? Why do you want to take out the last column?
Well, I'm just saying for the other machine learning algorithms, not the tree-based ones,
Okay.
you would have to, because the last column is dependent on the other columns, and then the matrix multiplication gets messed up. This was Anton's description of it.
Wait,
It made
I
sense
don't
to me.
understand what you mean by the last
So
column.
say if you've got 10 categories,
Yeah.
if you look at the first 9 categories, you can deduct what would be in the 10th one.
Ah, okay.
This is only in the case where there is only one thing per row. You know that one of the rows has a 1 in it, and all the other rows have a 0 in it. So if the first 9 rows have a 0, that last 10th row has a 1.
Yeah.
So you don't need to give it that 10th row. But that doesn't apply for decision trees. So
Okay, thanks.
as far as I know.
And so is getDummies actually identifying dummy variables, dummy columns, or what's that called doing the PD getDummies?
Oh, so PD getDummies makes a new Panda data frame, and it takes this variable and it treats it as a categorical variable. So wherever there is a new value that appears, it's going to put it's going to make a new column for that, and wherever the ID that has that value, it's going to put a 1 in there. This is important here. You can add a prefix to getDummies. I'm going to be using getDummies a lot, and there's going to be a lot of the same values. Like event type is also going to have a 1 in it. So if I didn't have this here, it would just make a column named 1. And event type would also try to make a column named 1, and it would get confused. So I make sure that I do a little prefix before each one. So I'm going to do the same thing with event type. Actually, there was one thing I wanted to mention. With locations, there are 929 unique locations in the train set and 1,039 unique locations in the test set. So already this is kind of like a little iffy. Like there's 100 locations in the test set that don't ever appear in the train set. So treating this as a category already seems to not have any benefit for these locations. So there already seems to be something to gain here if we're going to use this variable. In addition to that, there's 1,100 locations in the full data set. So there's also 100 locations in the training data set that are kind of just useless. They never appear in the test data set. But still, we're just going to keep it simple now and just get a benchmark. So we're just going to leave everything as it is and not worry about meaningless columns. All right, so if we look at the event type, there's 53 unique event types, which is a lot better. So with each event type, there's probably going to be a lot of rows for the machine to learn off of. And there's for some IDs, there's multiple event types. So we had to kind of handle that a little bit differently for the getDummies. And the way I did that is I just do getDummies on this category here, and then I group by ID and I just sum everything up. So ID 1 will have a 1 in event type 11 or E11 and E13. That seemed like a simple way of doing it. And I go through that code here if you guys want to look over it. So log feature adds another complication to this getDummies thing. It has 2 columns that seem to kind of be related to each other. Does anybody have any idea how you would deal with that volume column? So the way I did it was I just kind of I figured that log feature was the important column and that volume was kind of like a numerical value to put into that. Like volume definitely seems related to that log feature, and maybe there's like 2 log feature 68s for volume 2, and maybe there's some volumes that go up to 10 and even 100. So it's a very variable column. So I just did a dummy variable on this and multiplied this big matrix by this array. And that's here. Unfortunately, it doesn't have any ones in, but you would see like a 2 here or a 5 here or something like that if it had the nodes. There's also multiples in the same way there's events.
So now you would just reshape it. So as long as, I mean, initially I was confused if the volume corresponded to the log features or if it was a separate variable.
Right.
But then I think someone asked a question in the forum and they clarified that it did correspond
That was
to.
predictive in the end.
This log feature with the volume into it is predictive. I never even tried making this its own get dummy variable. It just didn't seem to make any sense to me. Like, why would this volume 2 be related to this volume 2 in any way? They're completely different log features. I didn't see that making any sense.
What does it represent, the volume?
Yeah, so you kind of had to play with your own interpretation and find some meaning in it.
Well, here you try to find a relationship between the log and the volume.
Here,
Is that what you tried?
I just assumed that the relationship was, I just assumed that a log feature is some log that somebody wrote in their notebook in real life, and then the volume is how many times that note was written down.
Yeah. So that value there is not numerical under the log feature.
The log
So
feature is not
that's
numerical,
just
the volume is.
Yeah.
That just means that that particular log feature exists and it has a volume which is on the right side.
It occurred twice.
So for example, the first one has the log feature 179, the first one in the table, and with volume value 1 for that log feature.
Seems a case where Kaggle is worse than real life because they're just pull up the client and say, what does volume mean? Yeah, if you're supposed to be applying a little insight here, but you have to guess. I don't know. It's kind of weird.
Doesn't it mean that let's say you're parsing your log, your system log, you'd find whatever they labeled as 68 twice inside the log?
That's what I was thinking.
That's kind of
So that's what I've assumed here.
Yeah.
And that is, reading through, that's I think what most people did, and that's what everybody did at the top. So that seemed to be the right way to go. I did the same with the other 2 types of data. I don't show all the charts. These are actually a little simpler. There's only 10 unique resource types and 5 unique severity types. And there's not even, all these severity types, they never appear twice. So there's only one severity type per ID. So that makes it very simple.
What does shape do?
Shape just prints out the shape of my new data frame. So this is 18,000.
Oh, okay.
I just needed to make sure, I wanted to, as I'm going along, making sure that everything's working properly, everything has the same rows. So I'm going to now connect it, I'm going to concatenate them side by side by side. That should work fine. Also, get dummies, I'm not sure if you guys know, it automatically makes whatever you're grouping by the new index, and it sorts it by that index. So I didn't need to sort any of the things that I group by. And I concatenate them all together, I save to file, and I put it into my XGBoost that I tune with my HyperOps script, which I'll get to after I do the next bit. And this already places, without doing really anything, any feature engineering, nothing really intuitive here, this already places better than half the people, 390 seconds. And I could have actually got this score a little bit lower. I actually just scored this today, and I ran a really quick XGBoost model. So I could have produced 20 of the models and then averaged my result over all of those, and it would have improved my score a little bit. So this is a good benchmark. All right. Yep.
Do you make these notebooks as you go along, just to keep a record of what you've done?
No, I just did this in the last couple of days. But I put it on my GitHub page, and I relearned a lot of stuff that I had forgotten. And I think it's going to be nice to go back and read, because it's kind of like, this is where I started out doing data science. This is kind of like the fundamental stuff, and I feel like I've learned it pretty well going through it over again. So
I think you said you hadn't used IPython before.
Never.
This is the first time.
Yeah.
It's pretty good.
I started a couple of days. Yeah, it's really cool. I like it. I've never even produced graphs before, so these are my first graphs I've produced.
Wow.
It's really easy in IPython Notebook.
Yeah.
All right, so the first thing I wanted to explore is this crazy location variable, as I mentioned last time. It really didn't seem like it was best suited to be a categorical feature. And I graphed the lengths, the location size. So if location, for an example, if location 200 appeared for 5 different IDs, I would call that a location size of 5. So what I found is that there are a lot, probably about half of the useful locations that have a location size of 3 or 4, of less than 4. And as a category, as a separate category completely, that is not that useful for the machine to learn on. Like, it's going to have only a couple data points at most, and a lot of these are probably no data points to try to create some sort of relationship with. And this is all these location variables that are just basically being put to waste. Some of these ones up here, I have played around with. I never ended up using them, but I think there are some people that managed to make use of, like, if a location has 170 data points in it, or this is all of the data, so maybe it would only have like 80 data points in it in the train set. But that's still a lot to learn off of, and I feel like including some as a category would have been useful. Anyways, so I'm curious about this location variable, and I got this plot off of this Dune Dweller Kaggle user, and it looks really nice. So green is fault severity 0, blue is fault severity 1, red is fault severity 2, and black dots are the things we're trying to predict. So, can anybody, like, what? Can we analyze this for a little bit? I've looked at this for a long time, so I kind of know what I'm looking at, but does this tell anybody anything?
What are the axes?
Yeah, say the X and Y.
The location is on the x-axis, and the ID is on the y-axis.
Do you have legend? Like, what do the...
So the green dots are fault severity 0,
Yeah.
the blue dots are fault severity 1, and the red dots are fault severity 2. And then the little black dots are the things that we need to predict.
So we're definitely seeing correlation in location.
Definitely, right?
Yeah.
There definitely appears to be groups, namely like here, maybe here and above,
Yeah.
that are acting, the location's acting similar to its neighbors, right? So it's really restrictive just saying that these are alike and they're completely different to everything else. It'd be much better to say that all of these are alike, maybe these are alike, maybe something in here is alike, maybe up here is alike. So, sorry.
So it looks like just say if location is above 550, then chances of having a severity 2 or red event is pretty high.
Right. Yeah. And just based on that alone, the machine would do better.
Yeah.
And it can probably use that in other ways as well. So yeah, so that the machine can do with just making it, going back to a numerical feature. That's what I kind of mentioned at the beginning, like just these simple cuts.
You mentioned that you didn't generate these QRS when you actually did the computation.
Right.
So would this knowledge have changed anything?
Well, I did treat it as a numerical feature, but that was just kind of trial and error.
Okay.
Yeah, I just spent a lot of time trying things, throwing it in the machine, looking at my results. I didn't do as well. All right, I'll try to change something else. Yeah.
Okay.
How many hours did you spend on it? Ballpark.
I'll do a quick calculation. There are a couple of weeks where I spent a lot of time on it. The weeks at the end, maybe 200 hours.
Wow.
And what was your final ranking?
63rd. But I would be able to reproduce my result in an hour. Like, I explored so much and found so little, but the things that I found were really meaningful. So you guys have no idea the feeling you get when you all of a sudden jump in score. You finally found that thing you've been looking for forever. It's addictive. I can see why people think of this. Did you guys ever go on April 1st to the
it was hilarious.
Yeah. There was this big notice that the site had been shut down by some big government agency for being too addictive.
Yeah.
And then you just need to click on it and go to the site. Yeah. All right. So, as I say, the location doesn't seem to be completely independent. It kind of behaves similar to its neighbor. So if you change it from a sparse and numerical feature, your score improves. You jump up 100 places just by making that one change. I did still spend a really long time trying to find a better use of this location. I thought for sure that because it's hard to see in here, but there's some locations that just have like a large portion of reds, and then a bunch beside it that don't have any reds, and then a bunch that have a lot of reds, and then don't have any reds. So I was looking for like spacing between these locations. I was really trying to find like mathematical like interpretations of like how can you predict when there's going to be a location that has a large number of fault severity 2s. And I don't think that there was one. I think it was completely random. But Dune Dweller came up with this weird method of like calculating the percentage of reds and blues or fault severity 1s and 2s for each location, and then encoding that into as a feature. You have to be really careful with this because if you're only dealing with your training data set, right? And if you're dealing with locations that only have 1 or 2 entries into the location, and you're telling the machine the average of these fault severities is 0, the machine is going to think that this is a really predictive feature, but in reality, you're just like, this is a leakage. That you're telling the machine that the average is 0, and there's only 1 or 2 in it. So like that data point has told the machine what it is, basically. So she has this really kind of innovative way of doing it, where she does out of loop. So she only fills it with predictions that are not made in the training data set that she's actually testing on. So like she splits it, takes all of those values out, and then adds the average overall, which is the average overall is 60% of these 60% of these are fault severity 0, 30% are fault severity 1, and 10% are fault severity 2. So she adds that and then normalizes it, and it improves her score very little. It improves it by 0.0008, which is like this number. Probably improves it her a couple spots on the leaderboard, but I really enjoyed her approach. I would definitely recommend reading over it, especially if you're interested in new ways to do feature engineering.
Do you know what she got for her final score?
She came 31st. Yeah. So now we'll kind of discuss the magic feature. So I noticed a big gap in the leaderboard, and a lot of other people noticed a big gap in the leaderboard. There was just like this big group of like 10 or 20 people that had around a score of 0.44 M loss, and then a huge gap, and the rest of these people had 0.50 and above M log loss. And so there must have been some feature that these people had found that was highly predictive that nobody else had found. So there was this huge chase in the leaderboard, and I spent a couple of days kind of reading every update that came into this forum about what people were talking about. And I eventually went back and read the description of the competition. And right around here, it says each row in the main data set represents a location and a time point. And this time point, there was never any mention of time in any of these data sets. Mm-hmm. And so I thought, well, how could time come into play into this data set? Like, how could they hide this information in there? And so I came up with a bunch of theories. This one actually doesn't refer to time. This is just kind of like lost information. So the number of total events, resources, or log features per ID. I tested that out. I tested the order that the events and resources and logs are plugged in. So if we look at here, so ID 1 has event type 11, and then after that, event type 13. Whereas some other ones will have event type 13 first, and then event 11. But once you make it sparse, they look identical, right? They'll just both have 1s in 11 and 13.
So there was a comment, you see that comment? Yeah. One person, yes, the ID increases for each new call.
I don't know what that is.
Well, meaning the ID numbers are monotonic and increasing with time, I think that's what they're saying.
Right. Well, here we looked at the IDs for the ID number, and you would expect to see some relation, like if you're taking horizontal slices, you would expect it to be different, right? If the ID number was important, which you don't seem to do. In fact, it looks very random to me. But that's not to say that it's that you can't learn off of that. Anyway, so I tested the order of the events, resources, and log features. I tested the ID in the train and data sets, which was just mentioned, and then I tested the order of the ID inside these files, and it appeared random at first. I'm afraid that I sorted it. I already sorted it before I went in here. So this last idea was the thing that actually did it for me. So if we reorder our data frame by the ID order that was in the severity type, you can do that by re-indexing the data frame. You will get this that comes out. So right away, all these locations are 1. So this data set is sorted in some way, right? It's sorted at least by location. There's no way that this data set was completely random. You wouldn't expect this many location 1s to be in a row. I also noticed as I scrolled through hundreds of these rows, I noticed another pattern. I want to kind of see if you guys can find it. So it's easier seen in larger locations. So this is all the IDs in that severity type order that are at location 821. Do you guys notice anything non-random? Yeah. So you're looking for anything non-random, right? Like if something is non-random, then the machine is going to be able to kind of predict off of that. And so it looks like the beginning, like the chance that all these are 0. Well, so maybe it's the location that just has a lot of zeros in it, right? So that was my first guess. So I went down here, I calculated the average fault severity, and it's about 1. So there should be, at most, half of these should be 1. Half of the total values should be 1s. So the chance that this is some random occurrence is very, very low. And I went and looked at all the other locations, and they all seem to kind of have this pattern. The first IDs per location all seem to be 0. So maybe this was the time. Maybe this wasn't just leakage. They may have just put this in there to like try and see how deep people look, or try to see if people look at everything. I don't know. The time thing, this is the only explanation for time that I can think of. So yeah, with this ordering, so now you can test it. With this ordering, the first IDs in each location have a higher chance of mapping the fault severity 0. So you can calculate. So you can create a new data frame. This is really fancy. A way to use group by. It goes really fast. And so we just have restructured. We've created a new column with this new feature that represents how far down each location it is. So like some of these smaller locations, you can see it a little easier. This 106 has 10 columns or so. Each time it goes down, it increases a little bit. So anything that's below like 0.1, that's going to be near the beginning of a location. And Dune Dweller again has a really nice visualization of this effect. And can you guys see this big clump of green down here? Highly predictive feature using this interlocation fraction that I just made. So I found this and plugged it into my machine, as I do with all the other features that I'm trying to see if they're predictive or not, and boom, already I actually think I was placed 23rd for a while in the contest.
So these horizontal lines, is that?
Oh, the horizontal. It's just whenever there's an even number of whenever there's a location where there's an even number of IDs, you're going to get something that goes to the same fraction. Yeah, so this is like 0.5, 0.75, I don't know, 0.8, I don't know. All right, so I spent the rest of the time trying to find relationships among, I'm just going to say now, this is the best score that I got. I was not able, I brought this down through averaging a bunch of different XG boost trees. I got it down to 0.43 and I placed 63rd. But these two things that I just mentioned, treating location as numerical and finding this magic feature, this is all I even managed to find, and I did very well. So.
You have a question? Could it be possible that one ID with high severity is preceded by a lot less severe in a small time period?
Yeah, that would be something that you could use as a feature. You would have to worry about leakage again because you would essentially kind of be predicting some of your, if you're only dealing with train data sets, because you remember you only know the fault severity for the train, right? So if you, I think you'd have to worry about leakage in that case, but you could find a way. I would reference Dune Dweller's approach of coding that in without introducing leakage, and that could be predictive. This is the kind of stuff that you kind of had to think about in these competitions, like trying to think of any way the data could be related to each other, especially with something like this where there's no missing data and there's really little room to like play around with features. You kind of had to look for out of the box stuff. So for the rest of the time I explored event type, resource type, and log feature, and severity type. And I found it useful, instead of looking at all my data in a sparse form, which is the only way I had concatenated all my data, like I couldn't tell which locations were to which IDs, right? Because it's just a data file of 1,500 columns. So I remade all my data files and made it, instead of making a get dummies, I just made it into a list. I group by it and made it into a list, and then combined all of that together. So I had a data file that looked like this. Much easier to read, much easier to kind of look for patterns. I looked at specific slices, so I looked at like everything that had event type 13 in it, and I made a new data file of that. I looked at that, and I noticed some really interesting stuff that I thought was going to be very predictive. So, actually, this is event type 11. So I noticed that every single time event type 11 occurred, there was a resource type 8. You can notice that if you go down, there's a lot of them. There's always resource type 8. I thought I was definitely onto something here, and there's over 200 of these.
How many event type 11?
I think there's like 700. And so rather than just eyeballing it, you can take my sparse matrix and you can sum the rows, or you can sum by columns, and anything that has the same sum at the bottom, well, not necessarily will be the exact same, but you can take a sub data frame, and then you can take a sub data frame of only event type 11s, which I did here, and then you can sum every column, and if the column with event type or with resource type 8 is the same as the length of your whole data frame, then it occurs every single time. That makes sense? So I spent a long time on this. This is actually not just event type 11. This is every single event type maps to one resource type. And you can kind of see that if we go down 13. So if we look at, 13 I think maps to, maybe 13 maps to 6. So let's find another 13. Okay, there's a 6. This is kind of what I did. 13, there's a 6. 13, 6. Yeah, so you can do the same thing with 13 and you'll find it maps to 6. And I did this, I had code that did this for all of them and kind of made a relationship dictionary and tried to figure out a way to use this into my machine. Also, every single log feature maps to one event type. So there's another layer of simplicity in here, or redundancy. This is what I had found, right? I had found redundancy.
So would that mean that you would remove the other columns if they're just already being mapped to? So you're saying log feature maps to some event, which maps to some resource, right?
Right.
So would it make sense to get rid of resource and event types since they're kind of plus? No, never mind.
Well, this is kind of what I was thinking.
Yeah.
Right, well, so in this case, for all of these event types 11, this resource type is redundant. This resource type is redundant because it appears every time. The machine's not going to, it doesn't care.
Is that going to, with XGBoost, is that going to cause some sort of artificial boosting?
I don't think so. There is a reason why this doesn't give me a better result, but it doesn't give me a worse result.
Okay.
It's just XG Boost is so good at finding these relationships on its own that it was kind of just like a waste of my human brain. Like it figured this out within like the first 2 seconds of it going, and I spent probably like 2 or 3 days mapping this relationship, figuring out exactly. I didn't go through. I had an automated system to like figure out which ones mapped to which ones, but it just proved to be a giant waste of time. So the way that I did it was like, for each log feature, there was one event that mapped to one of 2 resource types, and there were a couple of log features that mapped to like one of multiple events. So in those cases, you had to create a new feature and say, okay, which one it maps to. So I did that, and I was so disappointed I didn't get any improvement in my score. But I learned a valuable lesson in that XG Boost is really good at this type of stuff. And you kind of had to look for, when you're creating new features, you kind of have to like not worry too much about the relationships between the categories you already have. You need to kind of create new information.
So, did you try to encode? So, did you say you tried to encode anything? Like,
I did encode
create a new feature with, say, event type 11 and resource type 8, like, say, basically.
Well, that is basically event type 11. That's what that feature is. Event type 11 is event type 11 and resource 8.
Okay.
Because it always appears together.
So, what did you say you tried with as creating a new feature?
So there was, I think event 55 would sometimes map to event type, I'm just going to make this up, but it would sometimes map to event type 8, it would sometimes map to resource type 8, and it would sometimes map to resource type 6.
Yeah.
So is that predictive which one it actually maps to? I wasn't sure, so I made a new feature that had a 0 if it mapped to 6 and a 1 if it mapped to 8.
Okay.
And I removed the 2 resources that, I tried to remove the redundant information.
Okay.
And there were some other people in the forums that found this, that revealed it afterwards, that they found the same thing. And then there was a big discussion on how this is what XG Boost does.
So XG Boost is a tree-based method, right? So it could either pick up on the interactions depending upon what is the depth of the tree that you set, or even if you had just like the depth of the tree was just 1, because at every stage you have all the features available to select from. Mm-hmm. It always picks up these interactions, or there's always a chance for it to pick up these interactions.
Right, and it eventually will pick up the interaction, and it'll learn from that, and then.
Yeah.
So with some other methods, you would expect a performance increase doing what you did. Like if you weren't using XG Boost, if you're using another algorithm.
That's a good question. I have no idea. I'm not that familiar with. I'm really even not that familiar with XG Boost. As I said, I'm kind of just learning this stuff. I think one of us should at some point here do like a presentation on XG Boost and go through kind of like maybe step by step how it cuts its trees and what are the limitations of it, and like can it pick up, and what types of features can it pick up on.
Does anyone have a good explanation of what it actually does?
Yeah. From my limited understanding, when you grow a random forest, you're kind of doing so by take your data set, you take a subsample of the columns, and you grow a tree from all of those.
Right.
XG Boost doesn't do that simultaneously. I believe it grows one tree at a time, and it does so in a gradient descent type of manner, such that the forest you end up with is more optimized than the random forest.
Ah, cool.
I don't know if anyone wants to correct.
No, that's correct. Right. I mean, it's basically like gradient boosted tree. It's an implementation of gradient boosted tree.
Okay.
So every stage you grow a tree, and then you basically like fit another tree to the residuals.
Yeah.
From the first stage. So you know what I mean by residuals? Like basically, say your first tree predicts. Say it predicts 1 in place of 0, right? So that's where your residual is.
So you do repeatedly?
Right? Yeah, so repeatedly you fit trees, and then you keep pruning them.
Right.
This is to balance the variance, right? That's what you're right?
Yeah. So at every iteration, you fit a tree and you prune it. Then you fit another tree to the residuals. You prune it. So basically, then it has a chance of learning from all the cases that it missed in the first.
Okay.
In a given iteration. So it iteratively.
Yeah.
Like it puts more emphasis on the ones that it got wrong
Yeah.
for the next time round.
Yeah. So that's the gradient boosted tree.
So this,
And sorry.
this makes boosted trees a lot slower than random forests, right? Because you can't do them in parallel.
I know that you can do XGBoost is a parallelized algorithm.
So maybe what you're doing in parallel is you have a tree, and when you fit residuals, you grow 10 trees and you do that in parallel, and you pick the one that best applies the gradient. But you still do one tree that you select at a time because you're following gradient. And whereas with random forests, you can just throw one tree per core. If you have 1,000 cores, you're good.
Yeah. And at every stage, you have all the features available for selection, unlike random forest that you mentioned. Has only a random subset of features.
Cool. Yeah. So I have a little thing just for myself for improvement. There is discussion about feature creation here. Maybe I'll go to that. How are we doing on time?
We got 15 minutes.
Okay. I would like to talk about, well, actually, maybe I could just post it because it will be most useful for the people that are doing Python. My HyperOpt tuning script. But I got it on my GitHub, so you can definitely read it there, and I tried to comment it pretty well. So we'll just see if there's any room for a conversation with. How do I move this?
So the hyperop script is just to optimize the hyperparameters of the boosted tree model.
Yep. So this guy came fifth. He did the same thing with the order of ID, the log feature and severity type. That it's the same order. Converted location and log feature into numbers. So that's interesting. Yeah, I think there were some other people that used part of log feature as a numeric feature. Something like if it was above 203, it acted differently than if it was below 203 or something like that. So you would have maybe done the same graph that I did with location and found that like above a certain point it behaved differently than below a certain point. You can always use that as just like a one column feature and then keep the categorical feature as well. Don't lose that much information. Since the rows in this ID seem to be correlated with each other, he generated new features by shifting everything up one row and down one row, so that each ID would know what was above it and below it. So it would kind of be able to predict if it was like if it's a 0 above me, it's a higher chance of being a 0. Right. Yeah. So the 1, 3, and 4 all seem to do with that magic feature, though, for the specific case of this one. I believe, oops. This guy used a lot more features. I haven't read through these. I know he did well, though, so I just linked it here. He did 7th. And I'm just going to read through these. So this is what the magic feature is. This is magic feature.
Before and after fault severity. How would they figure that out? In the visualization? Why would they have thought to time adjust it by 1?
Well, if your ID if it's a 0 above you, or like let's say that your fault severities tend to come in packs. Like if there's a bunch of 1, if there's a 1 before you, it's more likely to be a 1 after you. So if you give the machine all the data of the one before you, it's going to kind of like it's going to try to predict the one before you, and then with that information, if it can predict that really well, and if it can know for sure that that's a 1, then it's going to have a better job of telling if yours is a 1. Does that make sense? So even if you're in a clump of like predicted things, that would be useful, because it might just be able to determine if some are 1s or 0s or 2s. This is kind of just basic stuff. I think this is mostly just basic stuff. Oh, there was also some people that did a weighted average of the 5 known fault severities before and 5 known fault severities after. That's kind of, that's a similar feature as doing like the one before and the one after.
And these last 2 features are the difference against the previous index.
Yeah. So this was kind of a weird challenge because of this leakage or magic feature. It seemed like a bunch of features were heavily reliant on the fact that the rows were not independent from each other. This is this graph that I used from James Waller.
So, one thing I didn't understand is why did using location as a numerical variable improve the performance?
Well, if you treat it as a categorical variable, it doesn't know, like let's say you are location 420 and you have 3 other things that are also location 420 or 430 or whatever. It has no idea that it should be looking at all of these to try to find some relationship. Whereas if you treat it as a numerical feature, it's going to treat this group as similar.
That's weird, because it doesn't quite make sense. It's not an order relationship in this, right? You cannot say location 1 is greater than location 2, like a numerical.
But you can say it's similar.
You can say they're close.
If there's anything that the machine can learn from, then it doesn't need to know that, like, it doesn't need to directly relate them. It just needs to say, okay, well, I'm going to treat anything 10 and below the same, right? And if it treats 10 and below the same, all of a sudden it has 100 data points to work with, as opposed to if you just have data category 1.
I never thought of getting closer.
Yeah, it would be interesting to kind of granularize the locations. Instead of having 1,100, you have 110. And you just say, if you're within 10, you're at 1 location. Mm-hmm. And then
I played around with this.
Yeah, you're getting rid of the...
Yeah, I played around with that. It was hard.
But so the first graph you showed with the exponential decay on location count.
Yeah.
You could have, that would have helped immensely in that kind of thing.
Yeah. I also had I created a cool data file. I created so many data files for this. Okay, it's at the top, thankfully. Where I have, this is a location here, and this is the number of fault severity 0s, 1, and 2. And so I just kind of like scanned through this, looking to see if there was anything the same. And this is where I found a bunch that had like a bunch of fault severity 2s, and then all the ones around that had nothing. That's kind of what led me to think that it should be categorical. But there's this group in here, 460 to 520, where there's nothing in 3 or 4, right? You'd think, okay, so it starts, well, there's that one exception, but there's a lot of data points in here. And remember, 30% are supposed to be fault severity 1. So these all seem to be acting similar to each other. If you treat it as a numerical feature, it can find this relationship. If you treat it as a categorical feature, it's just going to only look at these. It's only going to look at 10 data points for this one. So maybe I'll just quickly. I'll talk about my hyperopt tuning just a little bit. I think I put that on my GitHub page. Yeah. Always goes to this. This is Dune Dweller, by the way. I referenced her a lot when I was doing this. She does really good write-ups. I have her link in my data exploration one if you guys want to read up more on this contest. So this bit, I'm just loading in the data. And as we talked about before, I take my train, I say everything that's solid severity does not equal predict is train and test. So I've split it up nicely, so I can just deal with train from now on. I don't need to worry about any of the data that's in predict, right? Because I don't want to this is the only thing that I can train on, right? Does that make sense? That was wordy. So for hyperopt, you need to define an objective function where you return something that you want to optimize. In this case, I'm going to minimize this value. I'm minimizing the mean of scores. Each score is a run through of a machine learning with a certain type of set parameters. So this is the parameter space that I'm going to define. All these things, I actually link at the very top here, I have a detailed description of XGBoost parameters, so you can look up each of these, figure out what it does. Same with hyperopt. They go through a couple of examples of hyperopt. So you create a space of the parameters. For each one, you define where you want it to run from. So this is like the learning rate. I'm going to say it's going to go anywhere from 0.06 to 0.2. And I just looked up the default values for most of these and kind of just put it around that. So like for alpha, the default value is 0, so I said 0.5. For lambda, the default value is 1, so I said 0.75 to 1.25. Also figuring out which ones you need is important because this is a lot of things to tune at once. To get a really good space, you would need to run this minimization function like at least 100 times if you're trying to get good predictions of 7. So in the contest, I just used 3. I think I just used the top 3. And
you, run this again afterwards and see if it really did improve it with 7 over 3.
I ran it today and I got the 0.44 score with 7.
Right.
But I only use, so these numbers you can change. And so the thing that I submitted, it had to run for like over 3 hours as it's trying to train all this stuff. The problem is for each different parameter selections I do, this process takes a while. So this whole objective, this is going to run XGBoost 10 times. Well, the number of scoring rounds was I had set to 10. And each scoring round, it's going to take a split of 20%, make that the test, 80% make that the train, and it's going to evaluate how well it does on this test data set, and that's what it's going to return.
Right.
So it takes a while to run this. So you get to run it 10 times for each different parameter selection. And then I also wanted to average all these different models. And so for each model, I wanted to try to redo the parameter selection to try to kind of make it as random as possible. So I think I did 20 models, 10 rounds, or optimization rounds is a value that goes into the hyperopt. That's how many different parameters you wanted to test. You'd actually probably want to use more than that. For 7, you might want to use like 100, but that would take a really long time. But if you're going to sleep, you can just kind of like set it up.
Yeah.
Come back to a good result, letting it run all night. And so for the number of models that I average, I just add it to this list, and then each time I make a prediction, or each time I go through this whole process, I add my new prediction to this list, and then I concatenate them all and group by ID and just take the average. So yeah, this is huge for me. Learning how to do this was probably the reason I did so well in the competition.
So how long did this take? Did you time it?
It took about 3. Yeah, I have the time set up here. It took about 3 hours, but that was with 3 things. The forums, there was some discussion on how, like, apparently tuning the machine learning algorithm didn't improve people's scores that much, and stacking had almost no effect on people's scores. I think it's because of the magic feature. I really think it's just because, like, most of the features that they gave you were kind of insignificant compared to the magic feature, and you just had to use the magic feature in as many ways as possible, and you would get a better score with more ways that you used it. Actually, using extra trees as an ensemble improved people's scores. But that was the only usual machine learning method you could use. Stacking was out of the question, and random forests didn't improve it. Neural networks didn't improve it. Just extra trees for some reason. It's apparently the same in the BNP.
Yeah.
What is
Extra
it?
trees are really good. The BNP competition?
What about it? There is some leakage in there?
No. The using extra trees as an ensemble with XG Boost, it helps boost your score up.
Okay.
I don't know the reason behind it, but maybe they work in slightly different ways.
It's just in general, adding different models works better than adding the same model. Like averaging over several XG boosts doesn't do much. But the moment you add an extra tree with an XG boost, just two of them, so my score went up way higher. Like,
But there was talk, and random forest didn't improve people's scores on this one, and neither did neural networks for some reason. I know that normally, like the more models you use and averaging that, it's usually supposed to improve your score, but extra trees did, and none of the other ones did for this one for some reason. There's probably a good reason behind it, though.
I mean, I was wondering how does HyperOpt compare to other nonlinear optimization algorithms? I mean, has anyone here tried using?
We talked about that a bit last time. Some of the other ones, so a HyperOpt is completely, it's each time it picks new parameters to run, values to run, it does that completely independently from all of its previous results. So there's no sort of like gradient descent, like selection method here. It's almost like a grid search. It's like completely like a grid search. I think there's some higher optimization that they use, but I don't understand how they do it. The problem with some of the other ones, they're a lot better for time to run. Like they'll get there a lot faster, but they can get stuck in like local minimums, whereas there might be a global minimum somewhere that you'd only find with grid search.
Yeah, I mean, especially as your parameters increase, it would take a long time.
Oh yeah, I don't think I'd recommend 7. I just put them all in here because these are the 7 that I saw other people using.
There's a library called DEAP which does genetic algorithms, and there's a wrapper on that called scikit-deep, which takes scikit-learn models and crosses their parameters in a genetic algorithm fashion to learn the best ones. I'm wondering if that might be faster for large parameter sets, just because grid search and dimensions just exist.
Oh yeah.
But I've heard more about HyperOpt being used in Kaggle than anything else.
Yeah.
I don't know if that's just this group or in general, but it's clearly doing.
is it really just a grid search?
It's got to be more.
I think it's more than a grid search. I don't know how it's better than a grid search though. I know I definitely heard that it doesn't use previous results in its future parameter selection. So I don't know how it does better than grid search, but there's probably some crazy method.
So doesn't that mean using some other ones which do consider the gradient, or they're maybe like based on stochastic gradient or something like that?
There are other ones that do that,
which might be better than this.
Yeah, but like I said, there is a slight downside of those ones in that they can get stuck in local minimums.
Yeah, I mean.
So if you're really careful and know it inside and out, you can probably figure out a way to optimize that and make sure that you don't get stuck in a local minimum, like make your learning rate high enough, or
random locations or something like that on this grid space. And then
so it kind of
that's probably going to take a ton of time anyway. So
you can kind of you could do like a combination of the two. You could have part grid search, part this. That seems like
so. I mean, I actually don't know what are the implementational details for the optimization algorithms, but wouldn't something like stochastic gradient, I don't know if anyone has experience here with stochastic gradient, shouldn't it be able to not be stuck in a broken minima?
Oh, I don't know. I don't know that much about this yet.
Okay.
Stochastic gradient descent can be pretty prone to getting stuck in the middle.
Oh, is it? Are there any MCMC, like Markov chain Monte Carlo based things? Does that?
You can probably do annealing on the stochastic gradient descent to get out of those minima, but
because I mean, I wonder how it would be I mean, you need something better than grid search, right? Especially if it takes like a really long time to run your algorithm for one iteration.
Well, I've just found not the HyperOpt package, but another app called HyperOpt Scikit-Learn.
Okay.
And this one says something about the various search algorithms in HyperOpt. So clearly there are several of them, and they're not just grid search. But the HyperOpt page itself is not particularly useful. But I found this one.
Okay. I think I'll probably try with a small data set, say Iris or whatever, in R, and then just use a bunch of different optimization algorithms and see.
So this is one of the algorithms. This is the
Possibly a stochastic function.
That's part of the whole sentence.
Yeah. What does this mean?
Stochastic squared.
Right.
They don't even know.
Next level stochastic.
The HyperOpt TPE is what HyperOpt Scikit-Learn was referring to.
That's what I use. I'm pretty sure. Where is it? Where did it go? I used algorithm TBE suggest. That might be different. Oh, this would be a good one to type in. It was just here.
Apparently TPE is a Bayesian method. HyperOpt also uses a form of Bayesian optimization called TPE, which is a tree of Larson estimators.
Well, whatever it does a good job of it. Just like XGBoost.
So, are we ready to move on?
Oh yeah.
You finished your thing.
This is it?
Anything else to say about this particular competition? Remotely? And if not, we'll move on to talking about the next meeting.
Just thanks very much. That was really
Thank you.
Yeah,
Thank you very much.